Hi, geometry students. Today we're going to learn about the Isosceles Triangle theorem. And so let's get started. We're going to start with a proof warm-up. So this says that dx bisects FDE. So when a line bisects an angle, that means that it cuts it in half, two equal parts. So in this case, the reason that they said dx bisects FDE is so that we know now that FDX and EDX are congruent. So I'm going to start off with just reminding you that every time they give you information in the given, they want you to use that and definitely put it on your picture, draw it on your picture. But there's a reason for that. They're not just giving you something for the given and you're not supposed to use it. So we're going to start off with dx bisects. You always write this bisects angle FDE. And we also know that df is congruent to DE. All right. And that's just given. Okay, so based on what they gave me on the first line for the given, that dx bisects FDE, I now know that angle FDX is congruent to angle EDX. Okay, and number two, that would be definition of an angle bisector. And if you're writing the lines down, that would be from number one. The line of references. Okay, so what are we trying to prove? We're trying to prove that x is the midpoint. Well, I need to prove then that this line is congruent to that line segment. I also need to prove that dx is perpendicular to FE. Well, I can do that if the angles are congruent, because if they're adjacent and congruent, then they are perpendicular. So right now we just have this angle congruent to this angle. In the given, they also told me that DF, this segment here, is congruent to this segment here. So all I actually need to do now is say that DX is congruent to itself, and that would lend me to know that this triangle is congruent to this triangle. So I'm going to say that DX is congruent to line segment DX itself, and that's because of the reflexive property of congruence. I do want to just remind you of all the 5 ways that we know. Remember the 5 ways that we covered in the last lesson to prove two triangles are congruent? There's side, side, side. There's side, angle, side. There's angle, side, angle. There's angle, angle, side. And there's hypotenuse, leg. So those are our 5 reasons or ways that we would prove two triangles congruent. In this case, these two triangles are congruent because I have a side congruent to a side, an angle congruent to an angle, and another side congruent to a side. This side, dx, is in both of the triangles. See, if I were to split those triangles up, do you see that? This length would be the same in both triangles. So that's why we can say that it's congruent to itself. So now I can say on step number 4 that triangle FDX is congruent to triangle EDX, and that reason would be side, angle, side. So side, angle, side. So now I know that two triangles are congruent. Well, all of the parts are now congruent. So I could say then that FX is congruent to EX, and the reason for that would be CPCTC. CPCTC, corresponding parts of congruent triangles are congruent. So now that I know that this side is congruent to this side, X has to be the midpoint by the definition, or the converse of the definition. So I can now say that X is the midpoint of FE. And the reason would be 6 converse of the definition of the midpoint. Okay, now, lastly, I also know from CPCTC, corresponding parts of congruent triangles are congruent, that this angle in here is congruent to this angle in here. So therefore, I know for step number 7 that angle DXF is congruent to angle DXE. And that's from CPCTC. And I guess I could have put it with 5 if I wanted to combine those, but it's also good to separate your steps, even though it does make it a little bit longer. For step number 8, and my last step for this, I would say that DX is perpendicular to FE, and the reason for this would be congruent, adjacent congruent angles form perpendicular lines. And that's the converse of the perpendicular line theorem. Okay, cool. Okay. Isosceles triangle theorem. So we're going to start with the isosceles triangle theorem after that really super fun warm up. So the isosceles triangle theorem basically, or an isosceles triangle basically means that I have two sides that are congruent, and you have to at least have two sides congruent. These sides we call legs. So here's a leg. Well, that's actually a leg. And this is a leg. This is what we call the base. This angle here, which is in between the two legs, is called the vertex angle. And then you have this angle congruent to this angle, which we call base angles. Okay. All right. So that's what everything is. So the isosceles triangle theorem states that if two sides of one triangle are congruent, then the angles opposite those sides are also congruent. So meaning here's a side, it means this side is congruent to this side. Well, then their angle opposite, so that's that angle, and the angle opposite that angle here, then they're congruent. So basically if you have two sides of a triangle congruent, then their opposite angles are also congruent. And of course, the converse says that if you have two angles congruent, then the two sides are congruent. So we're going to prove the isosceles triangle theorem, which basically means you can't use the isosceles triangle theorem. So in order to prove it, we are going to start off saying that BA is congruent to CA. And that's given. We're also going to come in and we're going to draw an auxiliary line. And an auxiliary line basically means that it's any line that you can draw into a shape that helps you solve it for some reason. And those lines could be parallel, they could be perpendicular, or they could be, say, diagonals. They could be any kind of line like that. We are going to say that AD bisects BAC because we're drawing that line in. And I'm going to label that AD. And then it's going to bisect this angle here. Well, remember what bisecting an angle means. It means that it cuts it into two congruent parts. And so based on bisecting the angle, I can now say angle BAD is congruent to angle CAD. And that's the definition of an angle bisector. All right, so I have a side congruent to a side, an angle congruent to an angle. And I also know that AD is congruent to itself. So I'm going to say that AD is congruent to AD. And that's the reflexive property of congruence. And so now I can say these two triangles are congruent. Well, if the two triangles are congruent, then their parts are congruent. So I can now say that triangle BAD is congruent to triangle CAD, and that's because of side angle side. And therefore, if my triangles are congruent, my parts are congruent, and I can now say B is congruent to angle C. And that's from CPCTC. Now, keep in mind, we are proving the isosceles triangle theorem, which basically means from now on, if I want to use the isosceles triangle theorem in a proof, I can say that if I have two sides congruent, then the angles are congruent. Or the converse, which says if my two angles are congruent, then my sides are congruent. So, oh, I just did that. Okay. Corollaries of the isosceles triangle theorem. Basically, if you recall, these are a lot of things that we've already done, but if you have an equilateral triangle, it's also equiangular, which basically means if I have a triangle that has all three sides congruent, then all the angles are congruent. If I do have an equilateral triangle and I do have all of the angles congruent, that means that all my angles are 60 degrees. In addition, the bisector of the vertex angle, so remember the vertex angle is in between two congruent sides. So if I bisect that angle, that means I'm cutting it in half. Very, very important. This is, I think, huge right here. If you do cut this angle in half and you do have an isosceles triangle, what that actually does is it gives you this perpendicular to the base. And it also gives you this length here congruent to this length here. So not only does this line that bisects this angle up here, which is our vertex angle, but when it comes down, it's perpendicular and it cuts it into two parts. And this is so important. I'm going to say this again. This works for, this works for isosceles triangles, and this also works for equilateral triangles. So let me say that again. If I have an isosceles triangle and I cut this straight down, cuts this angle into two congruent parts, it bisects it. Not only does it bisect those two angles, but it makes this perpendicular to the base, and it also cuts my base into two equal parts. It also is true for an equilateral triangle, and those are pretty much the only two instances that this cuts this in half, where that angle will equal that angle. This makes a right angle, and then it cuts this length into two equal parts. And you're going to use that a lot in solving right triangles, right triangle trigonometry. So it is important to know that, really important to know that. And then the last corollary is an equiangular triangle. This comes from this here. An equiangular triangle is also equilateral. And basically what that means is that if my angles are all congruent, then the sides opposite those angles are also congruent. So we're going to start off with this, and this is in your packet if you have your packet with you. We know that BC is congruent to AC. We know that angle 1 is 140 degrees. And our job is to find the measure of angle 2, the measure of angle 3, and the measure of angle 4. So based on the isosceles triangle theorem, if you have two sides that are congruent in a triangle, then their opposite angles are also congruent. So we know that the measure of angle 4 is equal to the measure of angle 3. Okay. You also know from the exterior angle theorem that angle 1, which is 140 degrees, is equal. See this angle out here? That is equal to the sum of the two interior remote interior angles. So 140 degrees is equal to the measure of angle 4 plus the measure of angle 3. Well, we also know that 4 and 3 are the same. So I can really say 140 degrees equals 2 times the measure of angle 4. And then if I divide by 2, I'm going to get 70 degrees is equal to the measure of angle 4. And if this is 70, then so is this, because they're congruent. So now I also know that 70 degrees is equal to the measure of angle 3. And by the triangle sum property that all the angles in a triangle are 180 degrees, I can say that this angle 2 is 40 degrees. I also could say it's 40 because that makes a line, and therefore 140 plus 40 is 180. So I'd say the measure of angle 2 is equal to 40 degrees, and that's just like a flowchart proof. And then this is the justification of that, and you can see that. So we have another proof. BC is congruent to DC, okay? And we know that BF is congruent to DE. We are trying to prove that angle 1 is congruent to angle 2. I'm trying to prove that this angle here is equal to this angle here. For me to do that, I would have to prove that the two triangles are congruent. And the two triangles that I'm talking about are this triangle here and this triangle here. I need to prove that those two triangles are congruent. I do want to stress the fact that there are other triangles in my picture, and even though I'm not using them for this one, I do want to point out that there is this triangle here and this triangle here. Even though I'm not using both of those specific triangles for this proof, I do want you to be aware that they exist, and that even though I'm not using them, I could use it in a different proof. So first of all, I know that BC and DC, oh, this I already have these here. BC, I don't have that there, so let's write that down. BC is congruent to DC, and we also know that BF is congruent to DE. And this is given, G-I-V-E-N, okay. So let's write that on our picture. BC congruent to DC. BF congruent to DE. Well, number 2 is something that I think, remember, I'm trying to prove these two triangles congruent. I'm trying to prove this congruent to this over here. Don't discount that, do you see this right here? Those are two sides in a big triangle, right? So we actually know that triangle BCD, or I could say CBD, you can say it any different way, but I'm going to say BCD is isosceles. That's an isosceles triangle. Remember what the definition said? The definition of an isosceles triangle says a triangle is isosceles if it has two congruent sides. So BCD is isosceles. The reason that you would say that is the definition of an isosceles triangle. So if those are congruent, if the two sides are congruent, and it's an isosceles triangle, then I can say that angle B is congruent to angle D. I can say that right here for step number 3, isosceles triangle theorem, that says if the triangle is isosceles, then the base angles are congruent. Okay. Now, well, if I now have this angle here congruent to this angle here, then I have two triangles congruent by side, angle, side. So now I can say that my two triangles are congruent by side, angle, side. In addition to that, once my two triangles are congruent, then I can say one's congruent to 2. CPCTC. I guess I didn't put my givens in there. There's a given, and that one's given too. You actually can combine them into one. Okay. And that's done. So let's solve for x. It looks to me like this is showing that my base angles are congruent, which then means that the side opposite my base angle are also congruent. So you would say 3x minus 2 is 16. You would say 3x equals 18 and x equals 6. You divide by 3. For this problem, the sides are congruent, which then means my base angles are congruent. So those are both 65. And remember, the sum of all the angles in a triangle it adds up to be 180 degrees. So you have x plus 65 plus 65 is equal to 180 degrees. Well, 65 plus 65 is 130 degrees. and that equals 180. I'm going to subtract 130, and so I get x equals to 50 degrees. Okay, and let's see. Solving for x, parallel lines form alternate interior angles that are congruent. And so I'm just going to go around. Watch, 62 here, 62 here. If my sides are congruent, then the base angles are congruent. So those are both also 62. And then I have another 62 and 62. So x is equal to 62 degrees. Granted, I could have done something, let's say, with and found this side, this angle here, and then subtracted that from 180 because those are add up to be 180, but we didn't need to do that. We can just use alternate interior angles. Again, we have two sides are congruent, then the base angles are congruent. So that makes that 65. We know that's 65 because those are vertical angles. And remember, here's two sides that are congruent, which basically means their base angles are congruent. So that's also 65. And that triangle sum here makes 130 degrees from 180. So 180 minus 130 is 50 degrees again. So this is actually a really great proof. This proof is saying that first we're trying to prove a couple of different things. We're trying to prove that BD is congruent to CD. Well, I can do that by saying this triangle is congruent to this triangle. I'm also trying to prove that this is perpendicular to this. Well, I can do that by saying 3 is congruent to 4. And that means if they're right next to each other, they're adjacent congruent angles, which means that they form perpendicular lines. And that's the converse of the perpendicular line theorem. So let's see what we have to get started. We know that AB is congruent to AC. We also know that AD bisects BAC. BAC. It's really kind of important that you realize that they're giving you this angle as BAC. They did not say that it bisects this angle down here. So basically by saying that AD bisects BAC, they're saying one's congruent to 2. We also know then that AD it's congruent to itself. My two triangles will be congruent. Then all the parts are congruent. So let's see what we got to say here. We know AB is congruent to AC. We know that AD bisects BAC. Both of those are my given. There's my given. Okay. The second thing that we do want to, that's number one. And number 2, if AB is congruent to AC, then I can actually say that triangle ABC is isosceles. And you do want to say that it's isosceles, definition of an isosceles triangle. You do want to say it's an isosceles triangle before you use the isosceles triangle theorem, which basically says that angle B and C are congruent. Let's see here. Let's see. Let me erase that part. Sorry about that. So B is congruent to C, isosceles triangle theorem. Next, once I know that B is congruent to C, I'll give that 2 slashes. Let's see. BD is congruent to CDC. Well, I should have enough information already to prove these two triangles congruent. And I'm going to say that's angle side angle. And do you know what? I actually did not need to say that AD was congruent to itself because I already have angle side angle. So what I can say now is that the two triangles are congruent, and that's because of angle side angle. And once the two triangles are congruent, then I can say that my parts are congruent by CPCTC. So I'm saying in one step, I'm saying 3 is congruent to 4, which is going to lead us to this right here. And I can say that, what else can I say? BD is congruent to DC, and that's going to allow me to say that that's why it said it was a bisector. So let's see. I can say 1 is congruent to 2. I should have said that actually in the very beginning, once it said it was a bisector. So I'm going to bring all of this down. I think bring that down. Okay. And what I'm going to say first, before I say that, is that 1's congruent to 2. Definition of an angle bisector. If AD bisects BAC, then 1 is congruent to 2. So that's my angle side angle. That's where the angle, that's important to say first. And lastly, I can say AD is perpendicular to BC because of the converse of the perpendicular line theorem. Alrighty. So couple of quick equations. We know that's x. This is a line, and that makes that 80. And these are the same. 80 and 80 is 160, and 180, which is the sum of all my angles, minus 160 is 20. So x must equal 20 degrees. This one, we have 3x, x. This is the same because, again, if my sides are congruent, then the angles opposite them are congruent. So you have x plus 3x is equal to 180 degrees. 3, 4, 5. So I have 5x equals 180. So x is equal to 36 degrees. All right. And that's it. That's all I got for you for the isosceles triangle theorem. So I hope that helped you. All right, thanks.